Changes in the process location and the spread can lead to out-of-specification products. In this lesson, you will learn how to create an average chart and a range chart. And hello again to this lesson, which essentially has 3 learning objectives. But before we get to that, a short foreword. There are already separate lessons for creating an average chart and a range chart. So, how's this lesson different? In the separate lessons for the average chart and range chart, the warning and control limits were calculated for a non-interference probability of 95 and 99% respectively. In this lesson, only the control limits for a non-interference probability of 99.97% are calculated. This corresponds to a width of the limits of 6 sigma, so plus minus 3 times the standard deviation. Depending on the region or the respective country or various specifications, both the 99% and the 99.97% limits are used. Therefore, in this lesson, the focus will be on the 6 sigma limits, and this in combination with monitoring the process location with the average chart and the spread with the range chart. For those who haven't seen the other lessons, the most important basics are briefly repeated again. So, after this lesson, you should know the basics of an average chart and a range chart. Furthermore, you should be able to determine the center line of the average chart and that of the range chart based on the data from a pre-series. And almost most importantly, of course, you should be able to calculate the control limits for both control charts. This lesson is divided into 3 chapters. In the first chapter, we get an overview of the basics of the average chart and the range chart. In the second chapter, the process center lines of these 2 charts are determined based on a random sample, and in the last chapter, the control limits are then calculated. So, let's get started with a quick review of the basics of the average chart and the range chart. We take again the diameter of a piston as an example. Its diameter of 60.1 mm is the product characteristic that is to be monitored with the control charts. When we speak of the mean, we mean the arithmetic mean. This is calculated from the sum of all values divided by their number. There is also the median or central value. This is the value in the middle of the values ordered by size. The limits of a median chart are calculated somewhat different than those of the arithmetic mean. Finally, there is the mode. This is the most common value. As stated at the beginning, both a shift in the process location, this means a shift in the process mean, and an increasing spread can lead to product characteristics being manufactured that lie outside the permissible limits. As can be clearly seen here in the value curve, the spread in the first part is small. In the rear part, the spread is so much larger that 3 values are outside the permissible tolerance. A shift in the process mean, up or down, can also lead to characteristics that are out of specification. However, to not make this repetition too long, I would like to refer to the lesson on the trend, run or middle third at this point as other signals that a process might be out of control. To recognize an out-of-control process, it is possible to monitor, for example, how the mean value of the individual random samples changes and how the range of the same random samples changes. For this purpose, the control limits are selected in such a way that there is a 99.73% probability that the mean value of a sample, or the range of a sample, is between these limits. With a probability of 99.73%, the control chart does not generate a signal. With a probability of 99.73%, there is no need to interfere in the process. Hence the term non-interference probability. On the left side, you can already see the formulas with which the control limits for the mean chart and the range chart are calculated. Let's take a closer look at these next. If x bar is the mean of a single sample, then the grand mean is the average of the individual means. Thus, x with 2 bars, or uppercase M, is the center line for this process. Similarly, R is the range of a single sample and R bar is the mean of the ranges from each sample. The factors A2, D3 and D4 for calculating the control limits are taken from tables. These differ from other factors used to calculate the 95% or 99% limits. The mean values and the range are initially unknown. If the control chart is to be created for an existing series production, samples from the current series must be taken to determine it. If it is a new process, a small number of parts must be produced and measured specifically to determine this data. This process is called pre-series. And it's such a pre-series that we look at in this chapter and use the data to calculate the grand mean and the mean of the ranges. So, the diameter of 50 parts were measured and the results entered in the table on the left. On the right side, the individual values have been entered into a control chart for individual values. Their frequency distribution can be seen in the adjacent histogram. In all these calculations, we assume that the values are normally distributed. The bell curve laid over the histogram should suffice for us as purely visual proof of a normal distribution. The mean value was calculated for each individual sample and entered in the right-hand column. Thereafter, the mean of the mean values was calculated. This grand mean can be found at the bottom. Its value is 60.105 mm. This is the process center line. The same was done next for the range. For each sample, the range was entered in the table, and at the end, the mean of the ranges was calculated. R bar is 0.066 mm. The y-axis of the control charts must be scaled in such a way that extreme values can also be displayed in them. For the mean chart, the y-axis should therefore cover at least twice the range of the largest and smallest mean found. For the range chart, the area covered by the y-scale should be at least twice the largest range found. So, with that, we would have determined the two required parameters, process mean and range, from the pre-series. Both values, 60.105 and 0.066 mm, have been entered into the table and control charts. Both are a part of the further calculations that we will carry out in the next chapter. In this chapter, the control limits for the mean chart and the range chart are calculated, both for a 6 sigma range. The only remaining unknowns are the factors A and D. These are taken next from tables that can be found in the relevant literature or on the internet. A section of such a table is reproduced here on the left. For a sample size of 5, as in our example, we take the value for A2 as 0.577. For such a small sample size, the lower control limit on the range chart does not apply. For this reason, values for D3 can only be found in the table from a sample size of 7. For the upper control limit of the range chart, the value for D4 is 2.144. All values have been transferred to the middle table. If we now insert the values into the formulas for the upper control chart of the mean chart, we will find that this is 60.143 mm. A value of 60.067 mm results for the lower control limit. And finally, the upper control limit of the range chart is 0.14 mm. As already mentioned, due to the very small sample size, the lower control limit does not apply here. The probability that a value exceeds the control limits is less than 0.27%. When such an unlikely event occurs, it is an indication that the process may be out of control. The cause must then be found and the process readjusted if necessary. Both the average chart and the range chart can show such an event independently of each other, because with the mean chart, ranges in the process location are monitored, and with the range chart, changes in the process spread are monitored. Well, that was a lot of new information. Therefore, I would like to conclude by repeating the 4 most important key messages. The average chart monitors the centering of the distribution of data from the process. The range chart monitors the width. This is the spread of the distribution. The control limits are set in such a way that there is a 99.73% probability that no interference in the process is required. A value outside the control limits indicates an out-of-control process. A readjustment might be necessary. If you found this lesson helpful, please let me know and leave a comment. Thank you for that, take care and see you next time. Bye!